next year. All right. Then if you need invoices or something like that, please contact the general chairman, Alfredo. Okay. And I think that that was it. Now this information is already uploaded in the Indico, so you can check there. So with this done, let me start introducing our next speaker, our next lecturer, José Ignacio Illana from Universidad de Granada, Departamento de Física Teórica y del Cosmos, High Energy Theory Group there. So it is our real pleasure. He's not only a big expert with ample view on all these questions related to electroweak and flavor, so he's an optimal person to deliver this course, but also he's very experienced in doing this in the similar school in Spain and also in organizing the school. So we take advantage of all this together, and we are very happy to have Jose here. And he will be speaking about the electroweak standard model. First lecture today. We will have a couple of more lectures tomorrow. And at any time, you may ask questions. I will be checking the chat and all that. He also has exercises. The material of this course and first exercises is already uploaded on the Indico, so you can check there. And without further delay, I leave him the floor. Thanks a lot, Jose, again. Please, whenever you like.
Okay, then you can hear me. Perfect.
Yes, perfect.
So I'm very pleased to be lecturing at this school. It is my dream to be there, not virtually, but really. But okay, let's see whether things develop properly in the next years. So as Pablo said, I am lecturing for 3 days. I have 3 hours in front. And I decided to divide the course into 3, say, different parts. First is more general. So I would like to discuss, say, fields and symmetries. So what is the basic guidelines that lead us to construct the modern interacting theories, namely, first, of course, the Poincare symmetry, so the Lorenz and symmetries, and then the gauge principle. So this is a very important, say, paradigm for us today. Then I will discuss how some say difficulties realized to quantization of gauge theories that we have to learn. And then I will discuss an important feature of the standard model as a gauge theory, and is the fact that it's a gauge theory that is spontaneously broke. And this is very important to understand, as you know, how masses can exist in elementary particles. Then in the second lecture, I will just discuss the construction of the standard model itself. I will then show what is the gauge group, the particle representations, got all the interactions that you obtain just from the gauge principle, first for one generation. And I will discuss how to break spontaneously the some of the gauge symmetries of the standard model, how you construct the Higgs sector, how and what are the gauge boson masses, what are the Fermi masses. And then I will go into, say, more than one generation, beyond one generation. You know, we have 3. And I discuss then the Fermi mixings, not only for quarks, which is something that is well known, and it's also something that I think David Delepin will talk about in his lecture, but also about the lepton Fermi masses, in particular the neutrino mixings that already Avelino has talked about very nicely before. So I will just review just a few things that I think I consider important in order to describe the general framework of the standard model. Although leptons, that's why I put it in italics. I mean, neutrinos in particular, the masses of neutrinos are beyond the standard model, actually. And then I will discuss some phenomenological tests of the standard model. I mean, I will just discuss the Feynman rules, how do we obtain the input parameters, what are the main experiments that lead us to measure them, what are the observables, how important are the precise predictions, and how important are the relative corrections to understand the standard model, and in which shape is the standard model. So how good it meets the experimental constraints. And this is more or less written in the global fields. Okay, this is the program. So, okay, first I have some bibliography. these are my favorite, say, quantum field theory books, and then the last is just the particle data group webpage. By the way, I think this first lecture is already uploaded in Indigo, so you can follow it yourself. And I forgot to mention that I will also write some exercises in the meantime that I will have, that I actually have listed in a PDF file in Indigo. Okay, so first, you know that the building blocks of nature are not particles, are fields. Fields are actually extended objects. So this is something that is filling the whole space. It's not a punctual thing. It's not a point-like thing. And the ones that we are interested in, the fields we're interested in, are relativistic fields, because you know that in physics, the systems may have well-defined properties under transformations. I mean, under Poincare group transformations, rotations, boosts, space and time translations. So you can build what are first the building blocks are what are the representations of the Poincare group, and those are these fields. This is infinite dimensional representation. So they have scalar, vectors, tensors. You can recognize even there the relativistic metric. But you also have spinorial representations. You have the Weyl spinors, the left and right one, and the Dirac spinors that is a combination of all of them. So with these objects, you say construct. I mean, describe the state of nature. Okay, with these fields. Now, if you want to provide dynamics to the fields, you have to write Lagrangians, and these Lagrangians, of course, have to be invariant under these transformations. And the simplest Lagrangian you can build, for instance, for the free Dirac field, is this one, is the famous Dirac Lagrangian, that is written in terms of these objects that are spinors that have 4 components, not to be confused with the four space-time dimensions. And you know more or less everything about this Lagrangian. But the important point is this Lagrangian is first invariant under space-time Poincare transformations, all of them, rotation, boost, and translation. These are sacred symmetries of nature. And you know that whenever you have a continuous symmetry, and those are, Nether's theorem tells you that there are conservation laws. And in particular, for those symmetries, what you have, the quantities that are conserved are energy, momentum, angular momentum, etc. Okay, so if you go to the dynamics of this field, of this Dirac equation, of this Lagrangian, the dynamics is given by the principle of least action classically. This is implemented in the so-called Euler Lagrange equation, and for this field is the Dirac equation that you know very well. And the solutions are combinations of plane waves. Those there. These plane waves have positive and negative energy, and actually verify this, of course, this Einstein dispersion relation. Okay. Now, so far so good. You have only fields, but then you quantize these fields, and you promote this whatever field you have. For instance, in the case of the Dirac field, to an operator. And this operator, once you quantize it and you impose some so-called canonical quantization rules, if it is a fermionic field, because this representation contains a spin half integer, spin half particles. I mean, a spin half is a spin half representation. This you are say compelled to write anti-commutation rules, and in these anti-commutation rules, what you find is that these coefficients here, these combinations of these coefficients in front of the spinors of the well-defined energy solutions, are just operators that create and annihilate what we call particles and antiparticles. Those are the particles and antiparticles, are the modes, the quantized modes of the fields, and they act on the Fock space of Fermions in this case. No, so this is the A dagger Ks acting on the vacuum is just a particle, and the B dagger B acting on the vacuum is the antiparticle. Okay, and the operators A and B annihilate the vacuum. Okay, so this is what you need to construct whatever relativistic theory, but then you discover something that is very interesting, and is that on top of these symmetries, this Lagrangian is invariant under another symmetry that is not a space-time symmetry. It's an internal symmetry, because it has to do with changing the shape or the form of this of the fields. That is some invention of you want to describe physics, and this And this symmetry in this case is just a global U1 phase transformation symmetry. So if you take the field psi and you multiply, psi by the way is a complex field, if you multiply by this phase, then the Lagrangian is invariant. Okay, so again, the other theorem tells you that there is a divergenceless current, which is this one. You can compute if you know enough quantum field theory. It's not very difficult. And then the zero component of this current, when you integrate it over space-time, is the conserved charge. And this is actually a charge that for a U1 symmetry could be, for instance, the baryon number, the electron number, even the electric charge, as we will see now. Okay, so this is a global symmetry that you have in the Lagrangian, that you have it for free if you want. Okay, in the free Lagrangian. By the way, these charges here, when the fields are quantum fields, are actually operators, and this number that they put in front here, that is an arbitrary thing, as you may imagine. I put just a constant here. This is an arbitrary thing. Is what I will is kind of the eigenvalue of this operator acting on the state of particles and antiparticles. And you discover very easily when you build your operator that the action of the quantum operator, so the charge operator onto a particle is an eigenstate with Q plus Q charge, and the antiparticle has opposite charge. Okay. By the way, this is these dots here are just because of normal ordering. This is a formality that has to do with the subtraction of the infinite zero-point energy of a field, but this is just a technical problem. Okay. So far you have a Lagrangian that is invariant under global transformations, but it's not under local transformations. If you notice that if you, instead of doing this transformation to the field where theta, this phase, is independent of the point of the space-time, is dependent on the point of the space-time, then the Lagrangian, this Lagrangian, is no longer invariant. But there is a trick if you want to make it invariant. You have to add, you have to substitute the derivative in the Lagrangian by the so-called covariant derivative. So you have to introduce a field, it's a vector field actually, it's called a gauge field, that must transform in this way, so that if the field transforms this way, the derivative is covariant, in the sense that the variation of the change of the derivative of the field to another point of space-time is just given by the same thing times the phase in front. So that when you calculate the psi bar this last psi, this is invariant, and this is an important thing. So you can check in an exercise that this is actually the case. If the fields transform like this derivative is invariant. Okay. Then what you have done in practice is that you have introduced an interaction in the Lagrangian you had before. When you replace this derivative by the covariant derivative, you have added to the free Lagrangian exactly this interaction that is fixed by the symmetry. And this interaction is interesting, is nothing but the contraction of the nether current, the one that was conserved before, it has to do with the global symmetry, with the gauge field, okay, with the gauge field. And you see that the interaction between this field that before was free and the gauge field, that is actually the interaction, is proportional to a property of the field that is just the coupling constant that I will call here E, and the nether charge of the field, of the fermionic field Q, okay? So it's proportional to these things, E times Q, okay? Now, since you have introduced two fields, the fermionic field and the gauge field, you have also to introduce the kinetic terms for both of them. You have done it for the fermion field, but not for the gauge field. You have to put some gauge invariant derivatives on the fermion field. And the simplest kinetic term is this one that contains the so-called strength tensor for the field A mu that is familiar to you because it's exactly the same F mu nu strength tensor than the quantum electrodynamics. Okay, so this is actually the U1 gauge invariant Lagrangian for quantum electrodynamics, if you consider that this is just the Maxwell field. Okay, so this is the way you make symmetric fermionic field. Adding, I mean, you make symmetric locally under U1 transformations, and then you get quantum electrodynamics. You can do the same with say, scalar field. This is the kinetic term. You replace the derivatives by the covariant derivatives, and you get the scalar QED. It's exactly the same story. Okay, and you can think of okay, this is a nice idea. You have imposed a symmetry on your Lagrangian. In this case, this was a U1 local symmetry, and if you want to preserve it locally, then you have to add an interaction. So you say the gauge symmetry dictates the existence of an interaction. So you may think of having free fields with more general, say, global symmetries, even non-abelian, whatever symmetries, under whatever symmetry group G, that is given by a set of generators. You know what a Lie group is. I mean, you have a continuous symmetry. It's just parameterized by a series of parameters. This is just the manifold of the group, and this is just the number of these parameters. In the case of E1, it's just one, but you have may have n. Is contracted with a series of so-called generators. Okay, before the generator was just one, there was just one phase, and the generator was just a number. But now, in general, these generators here are Hermitian generators that verify this so-called Lie algebra. So they may not commute with each other, but the commutation relation is this one. It's not zero, but this is the structure constant of the group. Okay, and indeed, if the group would be abelian, this structure constants would be zero. Otherwise, it's non-abelian, and then two operations, two gauge group transformations do not commute. Okay. Now you can make representations of these gauge group elements. You can represent any of these transformations in a space. Of D dimension, arbitrary space, a finite dimensional irreducible representation. These are unitary because these generators are Hermitian. And then these D times D matrices, U, that represent this element, of course, they multiply itself, I mean, themselves with the same rules as the elements of the group. This is what is called the representation in group theory. And you can express this whatever transformation given the representation of the algebra, so the representation of the generators of the group in this dimension. Okay, so in general, you may have a multiplet of fields. For instance, several fermionic fields, D fermionic fields, and they may transform as a multiplet by whatever representation of the gauge group you are talking about. Okay, and this is the general idea. And you can do many. You can think of many examples, and actually, the first example is the one we saw. It's just one generator, and you have the generator is just the charge, and there is the representations are one-dimensional, and this is an abelian group. But you may have the famous SUN groups, for instance, the group SU2 and the group SU3, that are familiar to us because they are the one that will be needed for the standard model construction. The SU2 has 3 generators, n squared minus 1 generators. The structure constants are the Levi-Civita symbols. The fundamental representation has dimension 2. And the generators in this representation are the 3 Pauli matrices divided by 2, just because I decided, or one decides to normalize them this way. And there is for every representation, there is a famous one, which is that join for every group, sorry, is a famous representation that is the one that has the same dimension as the group. So it has the same dimension as the number of generators of the group. For SU2 has dimension 3. And in any case, this representation is the elements of these generators in this representation are given by the structure constants themselves. Yesterday, actually, or the day before yesterday, Herman, when he presented the SU3 group of the QCD, showed what are the structure constants of SU3, showed what are the fundamental representations, which are these 8 Gelman matrices, and showed that you, in general, can have the 8 gluons, the 8 generators, in the adjoint representation. And the generators in the adjoint representation are given by these structure constants, as I showed before. Okay. Now, the idea is that, as I said before, you may have a more general Lagrangian than this one. This is a free Lagrangian where you have a multiplet of fields, and this is again invariant and this under a global transformation where theta is not dependent of the space-time point. But if it depends on the space-time point, this is no longer invariant. You have to add a covariant derivative. The addition of, the introduction of the covariant derivative is done in this way. So you have to introduce as many gauge boson fields, right? As many gauge fields as generators you have, and you do it in this way. So this is completely analogous to the case of the U1, but before you have here a charge and you have a field, and this goes absorbed in the charge, in the field. And all these fields transform this way. It is the way that they transform in the adjoint representation. And you can prove that then, if you do this, the derivative is covariant. Okay, you can check that the transformation of the derivative is just U times the derivative of the field. Okay, so then this is invariant. This is an exercise you can check. Okay, and now you have a richer interaction between the fields forming the multiplet, this multiplet, and the n gauge fields you have introduced. And this fixed by the symmetry. It's again the contraction of nether currents, because all these gamma mu Ta psi are nether currents, and you can check that are the nether currents associated at the global symmetry. When it is local symmetry, they lead to the interaction with these gauge fields. Okay, and they are proportional to the gauge constant, to the coupling constant, sorry, G, the one that you introduce here. This is a property of the gauge field times the Ta, which is in which representation your fermion fields live. Okay, this is, for instance, the isospin in SU2, or maybe the color charge in the case of the gauge interactions. Okay, so it's the same idea. So this is a very fruitful idea, a very beautiful idea. And as I said before, you have also to introduce the kinetic terms for the gauge fields, but then a new thing shows up, and is that in the case of the non-abelian gauge fields, the gauge invariant kinetic terms for the gauge fields cannot be just this, say, partial mu w nu, partial nu w mu for every field. You have to add an extra term. Otherwise, the Lagrangian is not invariant. So you have to add self-interactions of the gauge fields with themselves. This, as you can prove, comes because if you define this object, this w mu nu, say, head, that is the contraction of this object, and this object is just by definition the covariant derivative acting on w nu minus the covariant derivative nu acting on w mu. If you do this, you realize that there is here, because of these two fields do not commute, there is a structure constant that when the say generators do not commute is different from 0. So what you have is that this object is clearly invariant. Sorry, this object defined like this, you can prove that this transforms this way under U. So this is invariant as you want. And then it contains interactions of the fields with themselves. You have first the kinetic term that would come from the W mu nu from this side here. This is just n times the kinetic term of the Maxwell field, if you want, one for every gauge field. But then you have also cubic and quartic interactions, self-interactions of the gauge fields among themselves. And they are proportional to the structure constants, and they are completely fixed. There are no more free constants here. They are fixed by the structure constant and the coupling constant of the group. Okay, so this is a very interesting idea. So in this way, you think nowadays that you can introduce any interaction of nature as a preservation of a local symmetry. You give me the symmetry, and I give you what is the interaction. Okay, but now when you go to quantize the gauge theories, a theory like this, of fields like this, you have to be careful, because then you realize that the basics of quantization has to do with the introduction of the propagators of the fields of your theory. And you know that the propagator of scalar fields, for instance, is just the expectation value in vacuum of the time order product of these two fields, the phi and its dagger, if it is complex. Okay, and this has to do with the probability amplitude of a particle created at the point y to be propagating until the point x where it is annihilated. So this gives you the probability amplitude of a propagation of a particle. So this is a key object in quantum field theories. Okay, and this is given by this Fourier transform of this object that is just the propagator in the position in the momentum space. Okay. Notice that this time order here is very important to preserve causality, and it has to do with this I epsilon prescription here. This is called the Feynman prescription. These are called the Feynman propagators. Okay. The propagator is in general the Klein-Gordon. Sorry, is the Green's function of, in the case of the scalar field, the Klein-Gordon operator. So it's the inverse, if you want, of the Klein-Gordon operator. So it's the object that when you act with it with the operator, give you the delta function. Okay. So the inverse of this in momentum representation is just 1 over minus p squared plus m squared. Okay. So I times this is by definition, just because we adopt this definition, this is just the propagator. It's the inverse of the Klein-Gordon operator. You can do the same with the Feynman propagator for the fermion fields. This is this expectation value is again the Green's function of the Dirac operator. This is very nice, and this is again the inverse of this operator, of course. Okay, so you can define the propagator of particles for scalars and for fermions, but then when you try to define what is the say the propagator for the gauge field there, so for the quanta of the gauge fields, in this case, for instance, the photons, then you enter in one problem. The problem is that if you go and try to invert the analogous to the Klein-Gordon operator or the analogous to the Dirac operator, that is this operator that you obtain just applying the Euler Lagrange equations. And this is just the Maxwell equations, if you want, to your field. This operator in front, you can try and check it, is given by an expression that is not invertible. You have to modify the Maxwell Lagrangian with this blue term I put here, so that you can define, and then this will give you this term extra in this Euler Lagrange equation. You have to modify it in order for this operator to be invertible. Otherwise, you cannot define the quantum version of this gauge field. Okay, the reason is very clear. If you try to invert minus k squared, which is the Fourier transform of this, plus k nu here, you will see that this is impossible because this operator is singular. It has an eigenvector, which is k mu itself, whose eigenvalue is 0. If you multiply by k mu this operator, you get a 0. So 0 is the eigenvector of this operator, so it is not invertible. But if you add this term, this can be inverted. You can check it and invert the inverse of this operator in momentum space is this object. Again, if epsilon, if psi here was infinite, this term would not be there. You would get a propagator that would be infinite, so it would not exist. Okay, so you may argue, okay, but if you introduce this into the Lagrangian of the gauge field, this is no longer the gauge field. This is another field. So this will not lead to Maxwell equations, for instance. This is a different theory. Well, this is true, but the gauge fields have a redundancy, have a symmetry. So if you replace the gauge field by gauge field plus a term like this, partial mu lambda, in the case of a U1 symmetry, the Lagrangian would be invariant. So you can always ask that, for instance, adding a term that has this property, you can always choose a mu field that has this property. This is the so-called Lorenz gauge, and in this gauge, particular gauge, this term would be relevant. So you still would have the same theory. So if you work in this gauge, you are doing really nothing, but you can have the propagator. So the lesson is that you have to fix the gauge in order to have a propagator of the particle. The reason behind this is just this redundancy here, and you have too many degrees of freedom that propagate here. You have to fix them. You have to fix a gauge, and then you will get a well-defined quantum theory. Okay. So this term will introduce something that you may think, okay, but I have introduced something that, okay, the physics should not be dependent on this term I have added, as long as I'm in this gauge, and this psi dependence here will appear in the propagator. But the propagator is not a physical object, so you are allowed to have a propagator that depends on the gauge. The physics will not depend on the gauge. So eventually, if you use whatever gauge with arbitrary psi, the physics will the dependence on psi in the physical amplitudes will drop out. Okay, and actually you may choose a gauge, one of these so-called arc-side gauges, that is a group of Lorenz gauges, where the propagator is simpler. And an example that, as you know, the simpler propagator is the one where you put psi equal 1, and then you remove this part of the propagator, and your life is easier. Okay, it looks like a propagator of a scalar field, but for every of the components of the 4 components of the gauge field. Okay, and there are other possibilities. Okay, great. And if you have an non-abelian gauge theory, well, remember that you have many fields. You have as many as generators you have in the theory. You may add so many gauge fixing terms as this, and then you may have the propagators like this. Unfortunately, this is not the whole story, and you can prove, and this is deeper quantum field theory, that if you have a non-abelian gauge theory, the gauge fixing like this is not enough. To gauge fix the theory, you have to also add Faddeev-Popov ghosts. This is something that also Hermann mentioned in his lecture, and those ghosts are actually a computational trick. They are not, say, physical fields. They are just something you add to your theory that are scalar fields that are anti-commuting. So this is a mathematical trick, and these fields here couple to the gauge fields in this way. They live in that joint representation, and they have this kind of coupling with the gauge field. So they are irrelevant for instance, for the QED, because in QED is a abelian theory, but they are not irrelevant for instance, the standard model of the electroweak interactions or for the strong interactions. Okay, and actually this if you don't add these ghosts with these couplings, you will not preserve the gauge symmetry at the quantum level, and this will lead to disaster. You will have a violation of unitarity, a lot of problems. And you can check, and this is a very difficult exercise, but this is a very interesting one. I can give you the solutions at the end if you need them. That unless you introduce these ghost fields in the loops, because they are virtual, they are just non-physical particles, you cannot have that at one loop the structure of this gauge propagator has this form, and this is the form that it should have in order to preserve the gauge symmetry, which is the Ward identity in this case. In order to preserve that K mu acting on this self energy is 0. If you don't add this interacting ghost here, the result will be will not have this property, will not be, so the gauge symmetry will be spoiled at the quantum level. Okay, so these Faddeev-Popov ghosts are very important. Okay, great. So if you want to have a gauge theory that is a quantum gauge theory, you have to introduce the recipe is just to get a symmetric Lagrangian, just taking your free Lagrangian, putting your fermion fields in a multiplet, replacing the covariant derivative, where you introduce as many gauge fields as generators you have in your theory. You add gauge fixing terms and Faddeev-Popov for them, and then you have a theory that is a quantum theory, which is that has the right properties. This is great and very inspiring, and this is, as I said, the gauge principle. But then you notice that, for instance, if you want to have a mass for one of these gauge fields, adding a term like this is the Broca Lagrangian. So this is the Lagrangian for a spin 1. So for a vector field. You see that this Lagrangian, you may see that this Lagrangian obviously is not gauge invariant. It's not invariant under transformation of the field that we have seen before. So, and we know that in nature, some of the interactions, in particular the weak interactions, they are mediated by massive gauge bosons because they are short range. So they need very massive particles. Actually, we have found them. They have masses of the order of 80, 90 GeV. So it is not possible that we have a theory that describes all the interactions, but these interactions are massless because we know they are massive. Okay. So, but then, okay, you may say, but then I introduce by hand this term and I forget about the gauge principle. Okay, but the gauge principle is the one that led you introduce these interactions. Now you cannot tell me that you forget about it. Okay. So you would like to have a way to say introduce the interactions from the gauge principle, maintaining the gauge symmetry, and then having gauge bosons that are massive at the same time without spoiling the gauge symmetry. But this means this seems impossible, but there is a clever idea that allows to do that. And this clever idea is the spontaneous symmetry breaking. Okay. In order for you to understand what is the spontaneous symmetry breaking, since this is a school, I just decided to do it in 3 steps. First step, I will introduce what is the spontaneous symmetry breaking of a discrete symmetry. Then I will go to the case of a continuous symmetry, but global. And then I will go to the case we are interested in, which is a gauge symmetry, which is a continuous symmetry that is local at the same time. Okay, so that has gauge bosons, the gauge fields associated. Okay, so and then you will understand what is the meaning of the spontaneous symmetry break. So the idea is that you just introduce a Lagrangian of scalar fields. For instance, the simplest case is you just introduce a scalar field, a real one. Okay, with self interactions. These are interactions, 5 squared, 4 interactions. If you calculate what is the Hamiltonian for this field, it has some kinetic terms, a derivative, plus some potential, self-interacting potential, that is this part here with the opposite sign. Okay, and now, okay, since the Hamiltonian and the Lagrangian are Hermitian objects or real objects, if this is a classical theory, this parameter mu squared and lambda must be real numbers. And since you want that the Hamiltonian is unbounded from bounded from below, so it has not infinite negative energy, you have to require that lambda is a positive number. But mu squared can be either positive or negative. Okay, if it is positive, this is the shape of the potential. If it is negative, this is the shape of the potential. So if it is positive, the minimum is just unique. It's not degenerate. It's the value phi equals 0. But if it is if mu squared is negative, the minimum is degenerate. There are 2 possible minima, and these 2 possible minima are the 2 minimal energy states, and that of course are connected by a symmetry. Because if you change phi by minus phi, of course you get the same energy, because this theory is invariant under this discrete symmetry. Discrete symmetry is in this case a Z2 symmetry. You change the sign of the field. Okay, so if this is a quantum theory, you know that the vacuum means the state from which you have to start your perturbation theory. So it's the state from which you excite the particles adding energy to the system. So, and the field, a quantum field, must be such that annihilates the vacuum. Okay, so the quanta of the quantum field must be such. So the operators, the annihilation operator of the field must be such that they annihilate the vacuum. But this phi field has a vacuum value, expectation value, which is different from 0. Okay, you see that this is different from 0. So the solution is that if you want that this is a quantum field, is that you shift the field, you redefine the field phi as v plus eta, where v is this value, whatever of this, either this or this, and you start the perturbation theory either here or here. You choose one of them. It doesn't matter because this is symmetric. And eta is actually the quantum field, the one that in the minimum of your Lagrangian, because this is your theory, has expectation value of v, but eta is 0, annihilates the vacuum. So this is the actual quantum field. Okay. If you write the Lagrangian in terms of this actual quantum field, you see that this is no longer symmetric. There is no longer invariant under the exchange of eta by minus eta. So there is a lesson. If I redefine the fields, I mean, at the beginning, the Lagrangian has the symmetry, but the parameters mu squared and lambda can be chosen such that, being the minimum degenerate, the ground state of the Hamiltonian, which is one of them, you can choose one of them, is no longer symmetric. You are either here or here, and then you spontaneously break the symmetry. You have to choose between one of these 2 possibilities. It doesn't matter, but once you choose one, you break the symmetry. And then something happens. What happens here? You may say, okay, but why do you see that this is a spontaneous symmetry breakdown? Because if I look at this Lagrangian written in terms of this eta field, I see explicit breaking. This is not invariant under eta. You have here terms like this cubic term here, that spoil this, say, symmetry under the exchange eta by minus eta. But look that the symmetry, even if you write it like this, is hidden here. So there is a remnant of the symmetry that you can see here. And the remnant is the fact that although you have 1, 2, 3, say, interacting terms here, you have only 2 parameters here that are free, say eta and v, okay? So this is not a explicit breaking of the symmetry because here there is a hidden symmetry, and this is the discrete symmetry, okay? Being this symmetry discrete, there is no further consequences onto the dynamics of the system. But if the symmetry would be continuous, there is the situation changes dramatically. Take now a Lagrangian with not a real but a complex field, and now this Lagrangian with the same, say, potential as before is invariant under a phase transformation because these are complex, and you see that this is invariant again. Okay? Now the potential has this form is mu square modulus of phi square modulus of phi to the 4th here, and this has this shape of this Mexican hat shape when lambda is positive, as it should be, and mu square is negative, which is the interesting case. Okay, then again you must rewrite the fields phi, the complex fields that are 2 real fields in principle, say phi 1 and phi 2. But let me write them in terms of excitations, eta and chi, over the actual vacuum, the vacuum which is the state of minimum energy. That is one of them, whatever that is lying along this valley of the Mexican head here. Okay, so you may choose, for instance, this one, like I did here, or you may choose the other one here, or whatever. For instance, you may choose v to the e to the I phi. You may put it anywhere, and wherever you put it, this minimum would be the same, and this would be a possible candidate to be the vacuum of your quantum theory. Okay, but whatever you do, what you get is that the Lagrangian, written in terms of the actual quantum fields, chi and eta, is a Lagrangian that now contains one field that is massless and another field that has this mass proportional to the vacuum expectation value. Okay, and what happened here is that once you have chosen one of these possible vacua here, I chose this, but you can check that you can choose another one. If you would have chosen this one, just replace eta by this and chi by this, and you will see again the same. You will see one field that is massless and the other is not. What happens is that once you choose one of these minima, then you break spontaneously the only symmetry that you have here, which is the U1 symmetry. You break the only generator you have here. And since you have broken one generator, you have a massless particle associated. And this massless particle is one of these scalar fields here, real scalar fields, the chi or the eta, one in this case is the chi, that remains massless. And this is the so-called Goldstone boson. Okay. You may also think, okay, but mu square was already a mass term. No, mu square, when mu square is negative, is not a mass term. Okay? Notice that it's not a mass term, it's a self-interacting term. And when you write the things like this, only one of these 2 fields, not both, so it's not this is not a mass term, gets a mass, and it's not mu square. It's square root of 2 lambda v. Okay, this is the result. Okay. Now, if you you may think of having a different symmetry, for instance, a SU2 triplet with the same Mexican head potential as before. This is invariant under this global symmetry. And again, with the same setup, and you realize that if you assume that if you choose one of the possible vacua, for instance, that this gets expectation value, you can put the v wherever you can put the v. Then you notice that the new Lagrangian written in terms of this phi 1, phi 2, and phi 3. Let me write phi 1 and phi 2 as this complex field, phi and phi dagger. What you have is that there is a field which is the phi, the complex phi, that you see has no mass. There is another field which is phi 3 that has a mass. Okay, and then there are some self-interacting terms. Okay, so what you have here is that the original Lagrangian that was symmetric under this global SU2 transformation is now only invariant under a part of the global SU2 transformation. It's just only invariant under E1. And notice that I can just transform the complex field phi with arbitrary phase q, whatever charge if you want, q, and phi 3 is real, so it has 0 charge. So this Lagrangian is symmetric under a global transformation U1, where this field is, say, chargeless, is neutral, and this has a charge q. So out of the 3 generators that SU2 has, only 2 are, only 1 is unbroken. 2 are broken. Okay, you have only 1 remaining. So since you have broken 2 of the symmetries of your Lagrangian, once you choose your vacuum, then you have that 2 particles get a mass. There are 2 massless gauge bosons. Sorry, 2 massless scalar bosons. Those are the Goldstone fields, and 1 has a mass. Okay. Now this is 2 because it's actually 1 complex is 2 real scalar fields. Okay. So this is the idea behind the Goldstone theorem. Okay. So the number of massless particles that you have after you break spontaneously the symmetry is equal to the number of spontaneously broken generators. Okay. Of the symmetry. Okay. The reason for this is very interesting, and you can check that you have a Hamiltonian that is symmetric under a group. It should commute with all the generators of the Hamiltonian, and by definition, the minimum energy of the Hamiltonian is just the vacuum. So the vacuum has 0 energy. Let me put this is the minimum level. So this means that since H and T commutes, it means that the transformation TA of the vacuum, so whatever transformation you perform on the vacuum, must have, of course, the same energy, 0, as the vacuum itself. Okay, but now 2 things may happen. One is that the vacuum is such that the generators, all the generators, annihilate the vacuum. Then, if this happens, the vacuum is non-degenerate. It's the simple case where you have just this single minimum, and then nothing interesting happens. But if the vacuum is such that there are at least some of the generators that do not annihilate the vacuum, that acting on the vacuum, this is different from 0. So those are the so-called broken generators. Then the minimum is degenerate. Why? Because of course, if you perform this transformation, since this is different from 0, for these generators, you will go to another state that is a different state to the original one that will have the same energy. So you will have a degenerate minimum. Okay. And now what happens is that if you do excitations of your scalar fields, you have particles excited along the flat directions of the potential, so those that are connected by these broken generators, these excitations, since they all have the same energy, do not cost energy. Okay, so all these excitations associated to the broken generators are massless. So that's why you have as many massless scalars as broken generators you have. So you have as many Goldstone bosons as broken generators you have. Okay, and now things become even more interesting when the symmetry is gauged. So if instead of having a global U1 symmetry, you have a local U1 symmetry. You have a Lagrangian as the one before, but now the symmetry is kept in every point of space-time. Okay, so this is invariant under transformations of this kind, but with theta depending on x. Why? Because I ensure it because I have covariant derivatives. I have introduced gauge fields here, and of course I have to introduce this part here as well. Okay, so this is invariant under this, as I said, and the fields transform like this. And then you put this term, of course, is invariant as well. This is gauge invariant, so I am allowed to write it. So, but what happens is that because I choose the case where mu square is negative and lambda is positive, the vacuum is again non-degenerate. Okay, and now you have, sorry, you have a degenerate Lagrangian. You have many possible states connected by the symmetry. So the complex field, you write it like this as before. This is just the quantum fields, eta and chi. Okay, and now when you write in terms of this eta, chi, and a mu, the original Lagrangian, something fantastic happens. It looks like a miracle. Okay, first, as before, you get one field, which is the chi, that is massless, another field, which is the eta, that is massive. No mystery on that. Okay, this is the Goldstone boson, and this is the scalar field that has a mass. Okay, but what happens is that first the gauge field that you had here before, that was of course a massless gauge field, now has picked up a mass term. This mass term, look, is proportional to the vacuum expectation value of the scalar field phi. Okay, it's proportional to this. Okay, so thanks to the coupling of the gauge field to these scalar fields, it picks up, the gauge field picks up a mass. Okay, and then there are another strange things here, a few strange things here. First, you have this cross term here that say connects the propagation. This is a bilinear term that connects the propagation of a Goldstone field and a vector boson field that you would like to remove, because this is not a diagonal Lagrangian with non-diagonal bilinear terms. And then, of course, I have not written, but I should have written some gauge fixing term, because the gauge fixing term I need if this is a quantum theory. Okay, but then I will first solve this problem, the adding of Lagrangian of gauge fixing term, and the removal of this cross term, adding an interesting gauge fixing term, which is this one. Okay, let me add this gauge fixing term. If I do it, I have introduced a term like this, which is the term you are familiar with. The cross term like this, which is just minus partial mu a mu ma chi here. Then you still have from here a term, which is this one, that adds up to the term I have added, and all together form a total derivative. So this term here that you have, the one that you have introduced in the gauge fixing term, and the old one that you have before, add up to a total derivative. And you know that in a Lagrangian, or you may know that in a Lagrangian, a total derivative does not change the dynamics. Okay, so this is irrelevant. Okay, so what you get is that you have a Lagrangian where you have first a gauge fixing term for this field that now has a mass, ma squared, ma defined as AQD, okay? And then you have the Goldstone field, chi, the Goldstone field chi, that has this equinetic term and has this mass term. Now the Goldstone field has a mass term, and this mass term on top is a mass term that depends on the gauge choice. So this is not strange, because this chi field, this Goldstone boson field, as you will see, is not a physical field, and it could have a mass dependent, a term which is dependent on the gauge. Okay, and actually I will show you that I can even choose a gauge where I can remove completely this field. Okay, and the other field, the gauge field, is a term that has, look at the pole here, has a mass that is no doubt proportional to the vacuum expectation value of V. So now this gauge field has a mass and has a propagator that depends on the gauge field, sorry, on the gauge choice. This is not strange. We know that this can happen, and this picks this term here. Okay, so you can even look at this in a different way so that you understand it better. Instead of choosing this parameterization of the complex field phi that has two say real components, eta and chi, that had say no zero expectation value in vacuum, you may add a field eta and a phi, if you want, zeta, like this one. Okay, if I choose this parameterization in vacuum, zeta and chi are zero. So in vacuum you have a v over square root of 2. This is expectation value of phi. This is legal. But since you have a gauge symmetry, you know that you can change phi in every point of space and time, multiply it by a phase. And this phase is I choose it exactly as to cancel this field here, so that if you choose this gauge, if you choose this phase in every point, you have removed completely this chi field. One of the two fields you have here, the chi, you have removed completely. You have gauged it away completely. Okay, so now you can see that if you do such a representation, the Lagrangian has again a kinetic term for the gauge field, a mass term for the gauge field, a kinetic term for the eta field that has a mass as before, and where is the chi or the zeta is nowhere. Why? Because I've chosen a gauge where, by the way, there is no gauge fixing term at all. I don't need it. It's a gauge that is called actually the unitary gauge. What I have chosen is a gauge where the psi parameter is actually infinite. It's like taking this psi to infinite. Remember that this would be like choosing a gauge where there are no Goldstones. This is the case where if I choose psi equal 1, I get minus k mu over ma squared. Okay, and this is exactly the Broca equation. So it's just the equation for a field that has a mass ma, spin one field, and there is no propagator for the other field. Why? Because I have just taken psi to infinite, and this field does not propagate. And you see again, this was a non-physical field, so I could remove it. I can even choose a gauge where it is completely inexistent. Okay, so now I have the final recipe. If I have a gauge symmetry, and this is the so-called Braut-Anglais-Higgs mechanism that it was introduced, as you know, more than 50 years ago. And the idea is that the gauge bosons associated with the spontaneously broken generators, they become massive. And the corresponding Goodby Goldstone bosons, those associated to these broken generators, are actually unphysical. And this means that they can be absorbed. They can just be taken out or not. It depends on the choice. You can choose the unitary gauge and they are completely removed, or you can keep another gauge, for instance, the gauge where psi is equal 1, and you have and you keep them. Okay, but those are non-physical particles. They could be Goldstone bosons. Okay, and the remaining massive scalars that I have introduced are the Higgs bosons actually. So you can call Higgs boson to all the scalar fields you have introduced, or you can call Higgs boson to just the ones that are remaining that are physical, the ones that have a mass. Okay, and those are the smoking gun that this mechanism to get to give mass to the gauge bosons is in action, if you want. Okay, so you can say that the Goodby Goldstone bosons, so these Goldstone bosons that you are there and you can remove, are actually eaten up by the gauge bosons that get fat, so they get massive and disappear. So they can be gauged away. They can be, you can choose a gauge where they are removed. This is the unitary gauge. Okay, and altogether the degrees of freedom of the system are preserved, because before spontaneous symmetry breaking, what you have is that you have a massless gauge boson that has 2 degrees of freedom, as you know, to transverse polarization of the photon, for instance, and 1 Goldstone boson. Forget about the Higgs boson, and 1 Goldstone boson. But once you break the symmetry spontaneously, what you have is that this Goldstone boson is eaten by by the gauge boson. Okay, and now the gauge boson becomes massive, so it has 3 degrees of freedom, and the Goldstone boson disappears. So 3 plus 0 is the same as 2 plus 1. The number of degrees of freedom are preserved. And I am running out of time, so I just finish right here, just saying that for loop calculations, you may think that it's easier just to choose a gauge where you have less fields. So choose a gauge where you don't have Goldstone bosons. You can remove them. No, it's better to choose a gauge like the case psi equal 1, because then the propagators are simpler. Remember that the propagators are just as simpler as this. You can remove this term, and you have the same propagator as before, but with a mass ma. Okay, and at the same time, of course, you shouldn't forget, because then you could spoil the symmetry, that the Goldstone boson must be included, but in the internal lines, not in the physical states. They are not physical states, so they can only appear in loops. Okay, and then of course you might think, if I have a non-abelian gauge symmetry, then you have to also when you break spontaneously the symmetry, this is what happened in the standard model, you may see that the ghost fields will pick up a mass as well, that is gauge dependent. So they are also on physical fields, and after the spontaneous symmetry breaking, and you can see that these ghost fields that are act like a scalar fields with anti-commuting properties, they pick up a mass that is proportional to the gauge boson mass and this parameter, this gauge parameter xi. Okay, and this is a very important result that once you have a gauge theory and the masses of your gauge particles are obtained by the spontaneous symmetry breaking, the theory is still renormalizable. This is the result by Toft and Veldman. This is actually the thesis, the PhD thesis of Toft after the supervision of Veldman, that in a sense provide the Nobel Prize to both of them. Okay, so and this is very important because if you have a renormalizable theory, and the standard model is a renormalizable theory because of this, all the ultraviolet divergences that appear at low level can be removed just renormalizing just a few parameters in the Lagrangian. Right? So this is a predictive theory. And what we will do tomorrow is with these ideas in front, with the idea of the gauge principle and the spontaneous symmetry breaking, we will build a theory, which is the standard model that consistently explains all the interactions that we have observed in nature and the masses we have observed in nature. Okay, this is the idea. So I stop here.
Thank you very much, Jose. It was a great lecture. I appreciate some features a lot.
Hello?
Let me ask if someone has questions.
I cannot hear you.
Can you hear me now? Can anyone hear me?
I can hear you.
Yes.
Okay, so Jose, can you hear us? Okay, that's a pity. Well, Jose?
Hello?
Jose? Okay. Now you can hear me again. Okay, so I was saying that it was great. Are there any questions? Meanwhile, can you hear me, Jose? Can you confirm?
I think I can't.
I can't hear you.
But Jose, do we have him or we lost him?
Él sigue porque sigue presentando. Sigue.
Sorry, I couldn't hear anything. Now I can hear you. Maybe you will tell me every time.
I'm relieved. Okay, so I ask for questions. I don't see any. Let me just make a comment while there are questions. So in some courses, one sees the extreme limit values for the gauge parameter, right? So one discusses only the so-called renormalizable gauges and the unitary gauge. But what you did, I appreciated a lot because you kept the gauge parameter, and at some point it was evident that the Goldstone was not physical because it must depend on this parameter. So I like this a lot, and I will do it the next time I explain this. I like it a lot. It was great. So I don't know if there are other questions or remarks. If not, I want to ask you something, but let me check first. I don't see any. So I will ask you something that was cast to Tony Peak in a similar course. It was a less advanced school, but on similar topics. And then the question was by one of my colleagues working in a different area in relativity. And then his observation was that more than a century of experimental efforts and theoretical understanding around the works of Ampere, Faraday, Coulomb that led to Maxwell equations, was now reverted, in the order. Now we have the equations starting from symmetry, and it was just this gauge principle. So what's your view on that, on this other way of understanding things much easier, much more elegantly?
Well, actually, this is a paradigm, no? I mean, it's just it's a recipe that it seems to be the right way to write theories. The interactions come from the preservation of local symmetries, and this is something that this was a discovery that was a very at the beginning. It was, as I think also Herman mentioned the other day, that when Young-Mills theories were written for the first time, they looked very interesting. But okay, who cares? Because all the fields should be massless, no? So, but eventually, when after the discovery of this spontaneous symmetry breaking, and even more when the discovery of the spontaneously symmetry broken gauge theories, are renormalizable, the work of Toft and Feldman, it became clear that this was just a great progress because, okay, you just can define a theory just defining what are the symmetries of the theory. And the idea of symmetry is a very inspiring one, because the symmetries are not only things that help you simplify problems, but now help you kind of decide what the dynamics of the systems are. No? So this is, and on the same way that you have the Lorenz invariance and the Poincare invariance, I mean, as a guidance to build theories, relativistic theories, you have also the Gauge principle, this kind of internal extra additional symmetry, as the complementary principle that altogether gives you the recipe to build whatever theory that describes the universe, even with interacting particles. Okay, so this is a very remarkable thing, and this is a finding. I don't think maybe this is not right, but this is the current paradigm. Okay. And it's true. I mean, at the beginning, when Maxwell wrote his equations, he was not thinking on what are the symmetries behind it. Actually, the only symmetries that were behind at most were the covariance, the Lorentz part of the symmetries. But there were these other symmetries that when they were just discovered, they were elucidated. It was just like an aha moment, no? An eureka moment. And this is, I think, it's remarkable. I cannot tell you nothing but that I am also admired by this spectacular, say, finding. But I don't know what else can I say about it.
I fully agree. It is to be admired. Thank you very much. I don't know if there are other questions. I'm checking. Okay. Not that I see now. So I would like to ask you to unmute your microphones and then thank clapping the great talk by Jose today. We will continue tomorrow.
Very much.
Thank you.
And then if any of you have questions, you can email them to me, and I will let Jose know so that he can discuss them or whatever. We will find a way to clarify them. So thank you, everyone, and we will reconvene at 4, right?
Right, Pablo, at 4 we will reconvene.
See you tomorrow.
Much, Alfredo. Gracias, muchas gracias, José. Nos vemos.
Hasta mañana.
Hasta mañana.